It's so free.
I really hate things, especially electronics. Like Star Trek Next Generation, where they talk to the computer. No, I don't want any computer talking to me, and I don't want to interact with any of them ever. Just no. Okay. Okay. So when's our exam? Tomorrow in the lab. Who's invited? My people. Okay. So you're all invited. Isn't that great? And the exam will officially start at 3:20 and go to 5:10. If you wanted to start earlier, let's say 2 or 2:30, stop by my office, and I don't think anything is going on here. Yeah, we're fine at that point. So if you want to start at that point, that's fine. Just let me know and I'll put you in here. I won't let you use your own calculator because they basically store too much information. And so what I'll do is I'll hand out our own calculators, like these, and those we use. The exam is designed to be an hour, but it's usually been my experience, most people take about an hour and a half because there's a psychological barrier of finishing the test and then handing it in before you feel comfortable with it. And that's just the way exams are. Let's see what else. What does the material cover?
Everything from the beginning to
Up to?
special relativity.
Yeah, special relativity will not be up there, but it goes up to that material. So that means that the last material that'll be on the exam is the projectile motion stuff. Questions? There'll be two parts. I call the first part one. Okay, this mask is old enough, kind of falling around. And well, I was so glad when these damn things are off. I think everyone will be. So let's see what part one is going to be. The short questions anywhere. They're going to be basically. They're not going to have like multiple parts like parts A, B, C, D, E, and stuff like this. It's going to be relatively simple to do, or straightforward to do without a whole lot of work. Okay, and this is a relative thing. What I think is not a lot of work, students will say, well, it was, but that's just because you're learning the tutorial. Then there's 6 of those. You have to do any 5. You can do the last one as a bonus. I don't care which one, just let me know. Now, okay, invariably when I do something like this, what do you think a lot of people do with the bonus? Leave it blank. Okay, if somebody is basically giving you free points, you don't leave it blank. That's just test strategy. That's just foolish. Try it, even if it's not right. I do get partial credit on it, so you can go from there. Let's see what else. Part 2 will be the longer questions, so kind of the big idea questions, and they'll have multiple parts like A, B, C, D, E, like probably parts A, B, and C, but probably not a whole lot past there. Okay. Any questions? Okay, so today all we're going to do are questions with special relativity. That's it. And then we'll finish special relativity today, and then tomorrow we'll start the new topic of dynamics. So we're going to start dealing with forces and why things move and Newton's laws of motion. And pretty much we stay with that for the rest of the entire semester. Just it gets more and more things get built up to it and stuff like this. Questions? Okay. So we started a problem last time. Yeah, somebody here on it. And we had this unknown thing. The unknown thing was going this way. No, it's going the other way. It's going away. And 0.9 parts C. Is that right? Oh, this is 0.9 C, I think. And I think our ship is going to 0.95 C. Okay, that's what I remember. Is that right? No. Okay. And so for part A here was basically find the velocity of the unknown object. According to an observer on the ship. Okay. So you do these problems, the hardest part is figuring out what all the variables are and who's, what is V, what is UX, what is UX prime, who's S, who's S prime. That's going to be the hardest part. Once you get that figured out, it's usually pretty straightforward. Okay, so to begin with, these velocities right here, who's measuring these velocities? These are measured by this observer here. Okay, so that means that the Earth observer is, what do we call the Earth observer? S. The little axis right through this fellow, and this is S. Okay, so who's S prime?
The ship.
The ship. So we'll call this then S prime. What does that then mean the 0.95 C is? That means that value is B. That's your value B. Okay, so the UX always refers to the object we're studying, the velocity of the object we're studying. What object are we studying? Our little friend there, the unknown, whatever. And so that is the 0.9 C is?
Yeah.
That's be UX. So this whole thing here, this is nothing but a convoluted way of saying find. Now, this whole thing here, all this means is find UX prime. There it is, done. Okay, now how do we find it? Last time we derived an expression, they had an equation. What was it?
It's found from
UX minus 3
over 1 minus UXB.
Perfect. Okay, does that make sense? And again, when you do this, you're never going to really, these C's, rarely will you put in a value as 3 times 10 to the 8th for the C value. It will almost always cancel if you're careful with it, or you're going to leave things in terms of C. Okay, so let's actually go through and do this. We did it last time. It's okay. So UX is our friend, 0.9 C. If this had been going the other way, what would this be?
Negative.
That would be negative. Okay. Minus 0.95 C all over 1 minus 0.9 C and 0.95 C all over C squared. What nice thing happens to the C in this bottom part?
Cancel.
Yeah, all the C's cancel. Okay, so I never had to worry about that. And what did we get last time when we worked it out? Minus 0.3 something?
3, 4, 5.
Now, special relativity wasn't true. Let's say all the special relativity stuff is crap. Okay, what would this expression here become?
Then you would use the Galilean
Okay, so this whole expression really just becomes
UX
that,
minus 3.
yeah, that top part. And what would you have for the velocity then? The UX prime? 0.0, negative 0.05. See. Okay, so you can see you're actually getting a different value of the velocity.
Very different.
Very different. Okay. Yes.
Yeah, I'm sorry, isn't that, I mean, that top part can be like used, but only if it's like somewhere like with speed that's like not nearly as close.
Okay, in almost everyday life,
Yeah,
okay,
yeah,
you would just use this part here.
yeah, but if when we're using like,
It's whenever you get velocity as close to the speed of light.
yeah.
That's when you're starting about this. And again, I gave you kind of a ballpark estimate for the velocities. When the velocity is good about what?
1/10 the speed of light.
About 10% of the speed of light when I start worrying about relativity. Okay. Any questions to that? Oh wait, it turns out there's a part B to this. That's lucky. Okay. It turns out this thing here, there's an alien now. How would I know it's an alien? Antenna,
Antenna.
1 eye.
one eye,
Ears.
point of ears. They have a self-destruct. So they set their self-destruct to go off in 10 minutes. So the alien sets the self-destruct to go off in 10 minutes. Question is, how long does that ship take to explode according to somebody on the Earth? I hope there's a part C to this too. I can't wait to find out. How long will it take the ship to explode according to the Earth observer? Okay, where's the boundary for that? Over here, it's over here. Okay, so what do we do? What kind of problem is this? This is a time dilation problem. So we have this delta t equals gamma delta tp. Okay, so we have a time here, this 10 minutes. What kind of time is that? Is that a dilated time or a proper time, and why?
would that be the dilated time?
Yeah, I can't wait to find out how this works. I've always wanted to take this class. Thank goodness, I've heard it's really cool. Okay, who's setting the 10-minute thing?
Oh, the alien is, so it would be proper time.
Yeah, so the alien will be on their ship. They set their little egg timer to go off in 10 minutes and pull the ship. You're at rest relative to it, so that's actually a proper time. This right here. This is proper time. So this guy right here is 10 minutes. Now, what is gamma? One over 1 minus v squared over c squared. Now, have to be a little careful here. This v is the velocity. It's not necessarily this v here. This is the velocity of the object you're studying. Okay, so we're studying this object here because that's one that's going to explode. So that velocity is going to be what? If you want to know relative to this person, that velocity is 0.9 c. Okay, so what we're going to have here. This here, again, the seeds go out, and we're left with this one here. I think this one is always 2 point something. This big number of 2.9. Okay. So according to the ship and the delta t, according to the Earth observer, because the Earth observer is going to measure dilate time, this is going to be 2.29 times 10. It's going to be 22.9 minutes. Does that make sense? Okay, what do you think part 2 is going to be? Find the time, takes to explode.
Find the distance.
We can come back to that one. Find the time it's going to take that object to explode according to the ship.
Oh. No, sorry, I'm tired.
So find this, let's see, find the time. And observe on the ship. Saying it takes the object to explode. So if you're here, how long would you say that takes that object to explode? So what would you do? Close.
I'm thinking. Wouldn't it be when you set it up to time proper?
Okay, so you set up the same way because there's no difference here.
Oh, okay.
What is their proper time still? 10 minutes. But now what's the difference here? If you're on this ship, you see that ship, or you see this unknown thing. Move with the velocity.
Oh, negative 0.345 c.
Yeah. You see this velocity here. So it's going to have in this case here, this gamma here. It's going to be the 1 over the square root of 1 minus 0.34 c, 3.5 c. C onto the square. if you do this. It's 1.065.
Mhm.
So if you work it out. Now to T, it's going to be this 1.065, 10, or 10.65 minutes. Okay. Not a gigantic difference. But definitely measurable. Does that make sense? Questions for that? Make sense? Now, Eddie asked a question about distance traveled. Okay, how far would the Earth observer say that object traveled before it exploded? This is the part D. Find the distance. The object exploded. Find the distance the object traveled before exploding. Meaning once the self-destruct was set, before exploding, according to an Earth observer. Okay, what would you do there? I'll start off by writing D. It's like the other way.
Is the traveler the one on the human spaceship or is the
This is according to somebody on the Earth.
Yeah,
So
but
we're
the
here, we're seeing this
traveler.
thing go over this way. How far does it travel according to us before exploding? After the timer was set to go off? You gotta be hint, this one's easy. Don't overthink it.
E equals VT.
Done. What is V? According to this person. 0.9 C. Okay, so this one here, you are gonna have to put in the 3 times 10 to the 8. Okay, how long does, according to you, how long does that ship travel?
2.9 minutes.
22.9 minutes. Okay, so this one was gonna be involved, we're gonna have to put, so this one, if you're gonna put it in all the details, you'd have the 0.9. Your C would be your friend 3 times 10 to the 8. You have this guy here, 22.9 minutes. Would that be it? Would you leave it like that?
6.183 billion
minutes to seconds.
Yeah.
meters.
Convert this to seconds first, and then you're good to go. Okay, so 1 minute. 60 seconds. Work this all out, it's gonna be star. Okay. Does that make sense? Questions?
Oh, I
Yes.
have a question. Why can it be just D equals VT? Like I thought it would have to be some fancy equation because of the speed of light and all that. Yeah.
No, Just distance equals velocity, if there's no acceleration, we're assuming that. It's just to be, you know, the distance that thing travels, okay? You know how, for how long,
Mhm.
equals VT. That's why I said don't overthink it. Sometimes things are simple things. Sometimes they're not.
But the distance that the alien perceived
What would you do
being
for that?
traveled, we would do the length contraction, right?
Yeah, you could do a length contraction on this way.
On what?
You could do a length, this right here is gonna be a proper length, because you would have like this big meter second space that this guy's relatives rest two. So this is a proper length. So this person would then see actually then that distance contracted. And so that's how you do that. Question? Let's do another one. Okay, I don't want to do your homework. Can somebody show me the homework?
Come up the one with the angle, the rod.
Well, I want to do an angle one, but I don't want to do that angle one. That's fine.
I like something.
Yeah. Yeah, that one's so cute.
The cats.
Yeah. My cats read all, I haven't told you that, but my cats read all my exams for me. I go the day before the test. I tell them what I covered. They ask little questions. They raise their little paws and they take little notes. Then I take my computer and I put it out at night. And then at the end, they hand me the pen drive. And then I scratch them and I feed them. And then that's, so I don't know what's going to be on the test. So I print it. It's like, wow, that's a really good question. Wow. I wish I could answer that. Wow. If I could answer this question, I'd be really smart. That's do a variation on this. Okay, so let's say here you are there. And let's say here you're this right here, you're going to be Silver Surfer. Good. Silver Surfer. Good. Okay. So here you are, your Silver Surfer. And this is your surfboard through space, and you measure it. So Silver Surfer measures the angle his surfboard makes in space. To be, let's say 6 degrees. So this is 6 degrees. Okay. Silver Surfer. Measures forward to be, let's say 2 meters, which is quite the surfboard. Okay. Okay, so an observer on Earth measures Silver Surfer's velocity to be 0.98 c. Let's make it a little more challenging. We're looking at this. So you're here on Earth. You see Silver Surfer from this way, 0.99 c.
What is the 60 degrees relative to?
So this is the XY axis in space. Well, this is the X axis like this. It's going to be picked up to 6 degrees like this.
Okay.
XY axis in space.
Okay. Just.
Giant line in space. Everyone